Okay. Hey, Gerda, how are you? I hope you're doing okay. Not so good. Oh no, what happened? You okay, Gerda? Oh, okay. That kind of sucks. Is it like a beginning computer science class? I'm gonna quickly turn the fan on here. Go ahead and write out your response. Oh, okay. So, have you tried kind of learning on your own? Because, I mean, sounds like you're having a tough time. I can tell. If it's, uh, if it's, if you're having a lot of issues with that, then yeah, it certainly sounds like it's pretty stressful. That sucks. Well, yes, that's true. You're doing pretty well in this class as far as I'm aware of, anyway. So that's good. Well, I hope I can. I know it can be tough for communication issues. Computer science is one of those types of classes you need a lot of uh, detail because computer science is just like I know math is a different language, but yeah, literally computer science is a completely different language altogether that you have to kind of interpret and kind of put together when you code. If it makes you feel any better, I pretty much failed my first computer science class. So, yeah, that went pretty all right. Let's just say, Gerda, that semester was the worst semester I've ever had in the history of semesters. Whew, that semester was not pretty. Okay. I'll be honest with you, Gerda, and you take it for what you will, okay? So, again, I would understand if you decide to drop the class and whatnot. So take what I'm about to say for what it will. But like, let's say you get your bachelor's degree or whatever in whatever you're doing, then that bachelor's degree is only worth 3 years after you graduate. Like, after 3 years, nobody cares about your GPA. They care more about your experience, about what you did with that degree. So, I mean, it's up to you about how you feel about your GPA and things like that. Like, I totally get where you're coming from. So, like I said, if you said, "Hey, I'll still drop it because I feel like I get a better grade the next time around," I said, "That's cool." I could completely understand that line of thinking. I wasn't the best student either, so um, you know, so I mean, I was just like, if it comes to worse, it's like, okay, my experience should trade more than just my GPA at the end of the day. So when I got a master's, it's just like, okay, my grades, there they are. Wow. Woo! Yeah. JTS, my dude, how are you? I'm doing great, my friend. At the end of the day, Gerda, it's entirely up to you about what you'd like to do. So, I'd support you either way. Oh, what the heck? Huh? Okay. Morning, Chase, or afternoon. It's hard to feel like I'm ruining my future. Well, okay, I got a story for you then, Gerda. I got a story for you. JTS, um, uh, yeah, for some reason it kept it at the 21st. The 21st was what I extended it to, I guess, and so you won't be able to open up any more assignments. I may end up. So here's what I'll do. All right, JTS. JTS, I may end up opening up those assignments near the end of the semester if you're willing to wait. So, because I need to have the assignments for Chapter 4 open, okay? we'll wait for another couple minutes here. So, I guess I could tell you this story, Gerda, and hopefully this will make you feel a little bit better. All right. So, the year, well, what year was it? Oh yeah, that's right. I remember now. The year was the beginning of 1998. Yes, I remember. It was the second semester of my freshman year. Okay, so I was trying to get used to college and stuff, and I was going to U of I at the time down in Champaign. Kind of living on my own, being a complete bum, yeah, a worse bum than I am now. Um, and I the first semester it went okay. Okay, I wasn't doing great. Okay, it was a pretty rough transition from high school over to doing U of I stuff. And so I remember my GPA was like um it wasn't great. It was like 2.4. It was, I had a tough time with some of the classes. I just had a tough transition time. And that semester, I just decided, you know what? Certain classes I decided to kind of blow off or ditch classes and had bad times, or some classes I really tried and I just couldn't get anywhere, such as the computer science class. I remember that computer science class because we were supposed to learn JavaScript, and the entire class was taught by a person who knew Pascal. And it's like, well, how am I supposed to learn JavaScript from somebody who keeps teaching me Pascal? I don't understand what I'm doing. I still to this day have no no understanding of what I'm doing. So what happened was is that I basically at that point it's like I couldn't turn down at that point full time. Otherwise, certain things, scholarships and whatnot. So I was like, okay, whatever. I'm like, okay, fine. I took the L for that class, and I was like, I remember walking into that final, and there was like 500 people in the room. I answered like half the questions on the final. I walked down because it's like stadium seating. I walked down to the bottom there, hand in my final with 500 people looking at me. I walk out the doors shut behind me, raise my arms up. I'm like, I failed. It's so great. It's so amazing. It was pretty bad. It was pretty bad. I had a physics class. My physics class is basically all I learned from physics because of the poor PowerPoint presentation, the guy just talking 5,000 miles an hour. I learned F equals ma, force equals mass times acceleration, and I learned nothing else. And I had no idea what the heck I was doing. So I was like, okay, fine. You know what? That's I'm like, okay, that sucks. So um, so I was like, all right, well, I remember what getting ended up getting a D minus in that class. So I got a D minus in that class. So as you could probably tell, I got an F in one class. I got a D minus in another class. Now, I did have a math class that semester, and that semester was, I believe, Calculus 2, and that teacher had no clue what he was doing. Absolutely none. I think we got through like a quarter through the syllabus, maybe even if we're lucky, a half, a third, maybe. And I learned much in that class, unfortunately. Um, yeah, I think he ended up giving everybody a B. So I was like, oh, okay. Um, so I was like, oh, that kind of sucks. Uh, So I was just kind of like, I took another elective class. I forgot what it was off the top of my head. I think it was the history class. I think I ended up getting a B in that class or something like that. Anyway, got my report card back at the end of the semester. Yeah, I got like a 175 GPA that semester. A 1.75 GPA that semester. And I got put on academic probation. So I was put on academic probation by the end of my freshman year because of my terrible second semester freshman year. True story. So, there's a little bit more to this story. This is still the part that still makes me laugh to this day. It's tough, yeah. But here, there's still a little bit more to this story. So it's like holy shit. Oh man, I'm on academic probation. Of course, the worst part happens, and that is my mom finds out. She gets a she gets a look at my report card there, and oh shit, I ain't gonna lie, she was pissed. Holy crap! She's like, I paid for this college for a year and blah blah blah, and justifiably so. So let's get something out of the way. She was completely justified for saying so. Okay, absolutely 100% right at the time. Okay, I'm scared out of my wits end. My mom is berating me for 3 straight hours, like 3 straight hours. She is just berating the living hell out of me. And like I said, it was justified, no question about it. Finally, my mom got super fed up. And there's something that you got to understand. If you're Asian, or heck, even if you're Hispanic, there's one thing that you fear the most of what your mom does, and that is if she picks up her shoe. If she picks up their shoe, you know you done screwed up. All right? Really fucked. You really fucked up. Okay? That means you fucked the pooch and you're going to have to pay the piper. So my mom picks up the shoe and I'm like, "Oh shit." I'm like on one side of the kitchen and I'm booking my ass to the other side of the kitchen just to run the fuck away from this shit. As she goes back, she slings back, she throws that shoe at me, and bam, straight to the back of the head. I'm like, oh god damn it. So I was I was just like, oh, that hurts so much. But even to this day, even to this day, was she 100% justified in doing so? You bet she was. You know, you bet she was 100%. I still remember that because I'm like, yeah, I'm not gonna disappoint my mom by doing not so good things. That was a harsh lesson I had to learn. If I had to learn it the hard way, so be it. The next semester after that, I did try pretty hard. I got a 2.8 that semester, but I realized that kind of environment for me, at least U of I with mass amount of classes. All right, I mean, seriously, I couldn't survive in that type of environment, so I went to a smaller school instead in Lake Forest College, and I succeeded very well over there. So, for people to say I'm ruining your future, no, there's always opportunities to claw back. Okay, trust me. You learn from those things that you messed up on. Sometimes they can be harsh, but I guarantee you that you know you can come back from those, and it's certainly possible to be a success. Like I said, I'm not the perfect person. I think that was a good wake up call for me. I still wasn't the perfect student even after that, but I did better. You know, and if it doesn't work out once, you try again, and that's what you got to keep on doing. I'm sitting in this position, being a professor, working at a college as an adjunct professor, loving the life that I do. I think you could be in the same situation that I'm in, Gerda. Maybe not in the teaching aspect, but maybe for whatever you want to be doing. So, there's something certainly to be said of uh, you not feeling totally, if you feeling bummed, I get that. I totally empathize with that feeling. But there is a, if you work hard, you can, there's always a silver lining. There is a rainbow at the end. So Latino moms and Asian moms really say control V control. Yeah, that's true. You get the little chancla out. I think that's what they call it. Chancla. Yeah, you done screwed up. So yeah, that was yeah. So I mean, college is a serious place, yeah, but it doesn't have to be like super serious. But at the same time, you gotta learn your lessons. Sometimes the nice way, sometimes the hard way. No problem, Gerda. I just hope you feel better. I'm on the same bench. Especially the blue one. Okay. I it's not easy sometimes, but you know what? I tell you, I learned a lot from that experience, and I'm just happy I can pass along that experience to you guys, where you guys can hopefully, maybe hopefully, find your way out of a certain situations that hopefully will make it a bit easier for you. That's it. Simple dimple. I promise you that. Easy peasy. I'll tell you this, it's kind of one of those situations for me, for me, speaking for myself, that I learned a lot more from failing multiple times than I learned a lot from just succeeding. So, failing for me really helps so I can know what to do the next time around. So, sometimes just for myself, I think that's just sometimes a lot better. But I can pass along any experience and knowledge along to help you in the long run. That's great. Okay. Oh man, I've been 15 minutes here. Sorry. Sorry, I kind of had to share that story because it was like, that's one of those things. It's like, success is not always born. Yeah, time for math. Success is not always born from constant success or constant constant positives. Sometimes negatives are anything can be undone and put back together. Okay. Okay, let's get started today. Welcome back to Thursday, end of the week time today. So today we're going to continue on here with section 4.4. Okay, you should be able to start the homework here today for chapter 4. I would like you to get started with that because the homework was extended out until yesterday. I guess, like I said, JTS, I could change those due dates once those things pass by. So probably near the end of the semester, I'll reopen up the homework again for everyone. All right. In any case, last time we talked about solving exponential logarithmic equations, at least part of it, and we didn't take a look at some other examples for exponential and logarithmic equations. So we're going to take a look at a couple of exponentials here to start with, and we'll take also a look at a couple of logarithmic equations. And then we'll get into section 4.5, which is more of the application side of things using logs and exponentials in some variety. Okay, so let's go ahead and do a few more examples here from previous. Okay, so we're going to start right away with exponential equations, and we're going to see exactly how we can do these type of problems. So more examples just need to be shown because there are a lot of different varieties. So that's why we're just kind of hopping right into it and be like, okay, we're going to use our exponent rules here and our logarithmic rules. So we'll reiterate kind of what we did last time, and we'll see what we're working with. So okay. Okay, so we have 7 to the 2x plus 1 power equals 3 to the x plus 2 power. Now, one of the things we talked about last time is if we could put it in the same base, then we could set the exponents equal to each other. The problem with this is that 7 and 3, well, you can't really express 7 in terms of a power of 3 that you know off the top of your head. And yeah, 3 unfortunately doesn't work that way either. So what we need to do is we need to be able to set these, again, we need to be able to solve for x here. But let's talk about the key about how to do so. Now, the big key here in these cases is if you go ahead and you just take, man, you know what? I'm gonna do this. Just put a text box here. Okay, so the key here in this particular circumstance is to take the natural log of both sides. Okay, so that's the key that we're going to have here in this instance. We're going to take the natural log of both sides. So all we're going to do here is take the natural log here and the natural log here. Okay. That's going to be our first step. The first step here is the most important step. Now the question is, why do we take the natural log of both sides? Well, if you remember, we can use the power rule here, and we can take each of these exponents and bring them out to the left. Okay, so that's what we're going to do here for the next step, is take each of these exponents, so 2x plus 1 natural log of 7 equals x plus 2 natural log of 3. All right. Okay, so next what we're going to do is we're going to solve for x here. Let's talk about how we can do that. So if you recall something that we talked about at the very end of class last time, and I know this was kind of subtly said, but natural log of 7 and natural log of 3 are just plain numbers. Like, you could put it in a calculator. You could figure out natural log of 7 is some rando decimal number. Natural log of 3 is, again, another rando decimal number. Okay, so what we're going to do here is simply distribute the natural log of 7 to both terms, and we'll distribute natural log of 3 to both terms as well. So let's see what we get here. So we get 2 natural log of 7 times x plus natural log of 7 equals x natural log of 3, or natural log of 3. We'll put that in, tell you what, we'll put it in parentheses so it's distinguished here. So it's not 7x, it's just natural log of 7 times x plus 2 natural log of 3. Okay? All right. So the next part here is, how do we go ahead and solve for x? All right. So how we can solve for x here is, what we're going to do is we're going to get all the x's on one side. We're going to take all the other numbers and put it on the other side, i.e., if we don't see an x, that's going to get moved over. If we do see an x, so basically we're going to, let's do it this way. Let's subtract by natural log of 3 of x on both sides, because that has an x to it. And then we'll subtract the number here, which is natural log of 7 on both sides as well. Okay, so this is what we have here so far. Okay, so this is going to be 2 natural log of 3 minus natural log of 7. Okay, can anybody tell me, from this step right here, what do you think we could do next? How can we solve for x? What is the next step here? This is kind of like the important part here, so kind of want to stress on this part. No rules for this one. No rules for this one. We're just trying to solve for x here, right? Divide natural log of 3. Unfortunately, I cannot do that here. I cannot, it's a good guess though, divide natural log of 3. Good guess, but I can't do that here because I have another term that has an x in it. This is why I asked this question. So that's okay. It's fine if you don't know. That's not a big deal. It's a tricky question, but it's one of those important points that I put out because of what people miss quite often. We did that already. We moved all the x's to one side. We're set to go and moving all the x's to one side, so we're good there, Planet. Okay. Now, in relation to moving all the x's to one side, there's one more thing that we can do here once we have that in place. And that is, what we're going to do here is we're going to factor, we're going to combine, but instead of combining, we're going to factor x. So we're going to factor out an x. That's what we're going to do. Normally we could combine there. If I had, say, 3x minus 2x, yeah, I could combine that, okay, as like terms. And these two are like terms. These are true. That's true. These are like terms, okay? But if we could also factor it out and still take the same like terms. So again, we'll have x times 2 natural log of 7 minus natural log of 3. And that equals what we have on the right-hand side here. Okay. And so then we'll go ahead and divide by that whole expression there. So this is kind of like the big thing I kind of wanted to talk about here. We're going to divide by that whole expression there to get our final result. Okay, and this is going to be our final answer for this problem. Okay, 2 natural log of 3 minus natural log of 7 divided by 2 natural log of 7 minus natural log of 3. Okay, so that's the key step there. We got to factor that x out. We factor that x out, we're going to be in good shape. All right, and then we're going to get our final result. Okay. All right. Any questions about that? That admittingly is pretty difficult if you're not aware to do that in that problem. So hence why I point that out. Well, I mean, it is a decimal number, so you can put it on your calculator and get a decimal, though don't forget to put the parentheses in the proper places. So, but if we're trying to get down to that point, then of course we need to know what what we take and subtract and divide and do all that stuff. So, I know that it looks ugly, but it does serve a purpose. I promise you that. What math is this? This is college algebra, Abby. You're welcome to join us and ask questions. Are there any questions about this example here? We'll probably move to the next example here, but any questions about this one before I move on? Ah, you're learning pre-calc. Great. Maybe some of this will be helpful for refreshing your mind. So exponential and logs are used in pre-calc a little bit. So I wonder if you got into matrices yet, if you're doing the matrix parts. So, though I'm pretty sure you've done sine, cosine, tangent stuffs. So, okay, let's move on to the next example here. Thank you for the follow, Abby. Okay. All right. So this next one here is going to look a little bit different than the ones that you've seen before. Okay, but the way we're going to approach it is going to feel a little similar. So at first it's going to look really ugly, but then you'll see exactly how we attack these problems. Okay, so this is our problem here. E to the 4x plus 5e to the 2x minus 24 is equal to 0. Now, admittingly, you look at this and you're like, ugh, this looks terrible. This looks like worse than peanut butter and squid put together. All right? In which case I would be like, yeah, that's right. I Food Wars that reference. All right, so got so what's the trick behind this problem? All right? What is the trick behind this problem? Let's talk about that. So the key here behind this problem is to use substitution. Substitution. Yeah. Okay, so we're going to use substitution using the middle term. Okay, so let's go ahead and describe what that means here in this particular case. Now take a look at what we have here. We have e to the 4x plus 5e to the 2x minus 24 equals 0. So what I'm going to do is I'm going to make a slight contention here. Okay, I'm going to play a little substitution game. Now, what kind of substitution game am I talking about here? Well, let's call it the letter U. They call it U substitution, okay? If you're going to go into calculus there, Abby, you're going to see U substitution again. Maybe not in this form, but certainly when it comes to doing integration. All right. We're going to set U equal to this middle term right here. We have e to the 2x. So that's what we're going to do here. We're going to set U is equal to that middle term right there, e to the 2x. Now you're probably saying, well, whoa. Time out. You set it equal to the middle term. What the heck does that even do? Okay, well, let's rewrite this whole expression in terms of U. Okay, so we're going to rewrite this whole expression in terms of this U that we just defined. Okay, and you'll see exactly why it's a little bit brilliant to do it this way. First, we have e to the 4x. Well, e to the 4x, if we square e squared, for example, that's e to the 2x squared, which means you can go ahead and use exponent rules. You can multiply 2 times 2. This actually equals e to the 4x. So this is going to be u squared plus 5 e to the 2x is u minus 24, which equals 0. Okay. So that's what we have here for the first part. Okay. Now let's take stock in what we have. We have u squared plus 5u minus 24 equals 0. Okay, so what can we do next with that? It's now a quadratic equation. So what can we do with that? What do you guys think? Solve with QE? I think you meant like what, quadratic formula there? Is that what you're referring to, Gerda? Okay. You can solve this using the quadratic formula here. Negative b over 2a. Negative b over 2a only refers to the vertex. I want to find the roots of this particular quadratic equation. We're not talking about vertex here, Chase. I want roots. So you have two options here, right? So think of it this way. I want to factor or use the quadratic formula. Okay. All right. We either factor or use the quadratic formula here. All right. So let's go ahead and put a little warning label here. Boop. Okay. Okay. So my contention is that this does factor. Can anybody tell me what u squared plus 5u minus 24 factors to? That's my contention here. Two numbers that multiply to minus 24 but add up to 5. What do you guys think? All right, spot on. That is correct. All right. So 8 and minus 3, that is correct. All right, so that's going to be u plus 8. Okay, and u minus 3. You guys are right on with that. That equals 0. So as you can see here, we're going to get two answers for u. U equals negative 8, and u equals positive 3. Okay, that's what we have here in this instance. Now, we're not quite done just yet, and that's because of the fact that, well, we have a definition for u here. That was this guy right here. U is equal to e to the 2x. Remember, our goal here was to solve for x, but we used this u substitution as a medium to hopefully put 2 and 2 together. So here we have e to the 2x equals minus 8, and we also have e to the 2x equals 3. Okay, now I'm going to point this out as well because this is very important for this. E to the 2x minus 8 is not possible. Okay, and this is because exponential functions can never be negative. Okay, so remember, this can never be negative here. Okay, that's how it works. All right, so if you try and take the natural log of both sides, for example, you can't do the natural log of, like, say, minus 8. That's not possible. Okay, now for the second part here, let's take a look at that. We want to be able to solve for x. So what we're going to do is we're going to take, once again, the natural log of both sides. Let's take a look at what happens when we take the natural log of both sides. Now, natural log of e to the 2x. Can anybody tell me what that's equal to? On the right side, we have natural log of 3. But what's natural log of e to the 2x? There's this property we used from before there. Yeah, so I just want this part here. Natural log of e to the 2x. 2x natural log of e, okay. Well, what's natural log of e? What's that? What is natural log of e equal to? I agree with you, Gerda. Natural log of e is equal to 0? Whoa, careful there, planet. Try that on your calculator. Natural log of e. You guys can put that in your calculator there. Natural log of e is equal to what? All right, guys, this part is pretty important, so I'll wait. 1. That is correct. So in effect, what has happened here is that natural log and e, we use the property here that natural log and e will pretty much cancel each other out. Thus, it leaves you with just the exponent left over. So we're left with 2x equals natural log of 3. And that kind of goes back to what Goethe said. It says 2x natural log of e. Well, natural log of e is another way to write that is 1. So it'll be 2x times 1, which is just 2x. We go ahead and divide by 2, and that's going to be our answer. Natural log of 3 divided by 2. All right, any questions about that problem? No? Okay. Okay, so next thing that we're going to do here is we're going to go ahead and do the next problem here. Again, now we're going to transition from exponentials. We're going to transition over to logarithmic equations to solve for x. So let's go ahead and do that. All right. So we'll start off with something nice, and then we'll work our way up. Okay, let's start off with this. Log base 2 of x plus 50 is equal to 5. So what we have to do is go ahead and solve for x in this particular equation. Now, the things that we kind of have to focus on in this case is if you could look back at your notes, and I'm going to find out which question I put that under specifically. Not that one. It's back in section 4.2, I believe. Okay, so if we go back to this question here, what are some properties of logarithms to remember? We talked about several of those properties back in section 4.2. We're going to be using those properties that we talked about for in logarithms, as well as the rules that are in the next section over. Again, the power rule, quotient rule, and the product rule there. So we did talk about those, but again, we wanted to also use the properties of logarithms we talked about back in section 4.2. So what we're going to use here specifically is if for us to go ahead and find out how to solve for x here, we're going to use one of the following properties here. So again, we could use, remember that log base b of b here is equal to 1. That was one property. Log base b of 1 is 0. Okay, so that was another property. B to the log base b of x equals x. And if you flip it around, x to the log base, oops, wrong way, sorry. I meant to do it the other way. There we go. Log base b of b to the x is equal to x. Okay, so whereas you have this definition of kind of canceling out. So what you're going to see me do here in this case is I'm going to use one of these properties here to solve for x. Actually, you guys can tell me which one of these properties here, the first, second, third, or fourth property should I use in order to solve for x in this particular problem? What do you guys think? 1, 2, 3, or 4? Which one should I use? fourth one. So do I have a base? Do I have the same base over here, drivers? So I have log base 2, but do I have 2 to some power where I can cancel that out? So that's the thing you guys got a question here. I have log base 2, but do I have 2 to the x power to cancel that out? Over here. I don't have a 2 there. I just have x plus 50 there. So I don't think number 4 is going to fit. It's a good guess, but not quite. So if it's not 4, what else could it be? Could it be 1, 2, or 3? We have log base b of 1 is 0. Where are we using that? I don't see where we're using that part there. Now you've limited your choices to numbers 1 and 3. So we're down to final 2. Is it going to be number 1 or number 3? Number 3 is correct. Okay, good. Woo! You're now seeing 1. Okay. So let's go ahead and take a look here, and I'll show you why it's number 3. Okay, why is this number 3? What are we going to do to match number 3? Now this one here may seem a little strange, but remember, everything in algebra here is always a balance. So since everything is a balance, well, what I'm about to do is also a nice balancing act. So what I'm going to do here is I'm going to make this entire thing, log base 2 of x plus 50, I'm going to now make that an exponent. An exponent of what per se? I'm going to make that an exponent of 2. However, if I make this whole thing an exponent of 2, then guess what? I'm going to make that other side also be an exponent of 2, 2 to the 5th power. Remember, as long as I balance stuff out, okay, I can do it on both sides. No problem. Easy time. Easy clap indeed. So, in this case, 2 and log base 2 will cancel out, and that'll just leave us with the left-hand side of x plus 50. On the right-hand side, we still deal with 2 to the 5th power. Let me see what that becomes. So 2 to the 5th power is, what is that? 32? Yep, 32. Go ahead and subtract 50 on both sides. And so here we get x is equal to negative 18. And that's how we can acquire our final answer for that. Okay. Any questions so far? Okay. Any questions? No? Okay. All right. Now, let's focus on the next question here. I'm going to leave these up here, just in case if we do need to use them. Also, don't forget your product, quotient, and power rule there. Those will also play a part, possibly. Okay, so this is our next question here. Log base 3 of x plus 6 plus log base 3 of x plus 4 is going to equal to 1. Okay. And once again, we want to solve for x here. Okay. So let's talk about one of the key parts here in this problem. Where are the 4 or 5 notes located at? The 4 or 5 notes are located with the 4 4 notes. So it's 4 4 and 4 5 here together. They're all on the same sheet. You can find that on D2L there. Okay, so let's talk about the key here first. The key is to use log properties to combine into one log. Okay, let's make that slightly a bit smaller. There we go. Looks a little awkward, but okay. So we're going to use log properties to combine into one log. That's what we want to do here. Okay, so I want you to take a look at this first part here. In this first part, we have log base 3 of x plus 6 plus log base 3 of x plus 4. So if we have those two, we're adding together. What property can we use here in order to make that into one log? What log property can we use to turn that in from 2 logs into 1 log? So, okay, so we could use the first log property there of the product property, right? So let's use the product property here in this instance. So let's do it. So we're going to get log base 3 of x plus 6 times x plus 4. Okay, is equal to 1. We're going to go ahead and multiply x plus 6 and x plus 4. Okay, so we're going to have log base 3 of x squared plus 10x plus 24. You can go ahead and FOIL that side. You can FOIL this out here. You'll get 6x and 4x and 10x in the middle. Okay, so we went ahead and did that. There we go. All right, now what we're going to do next here is do what we did in the last example. In the last example here, we're going to go ahead and put a 3 out here. So we'll have 3 to that power and 3 to that power. That way we can effectively cancel out the 3 and the log base 3 and just leave what we have left over. And on the right side we have 3 to the first power, which is a straight up 3. Okay. All right. Okay, now we need to go ahead and solve for x. So let's go ahead and solve for x here. All right. So solving for x here, we first got to subtract by 3. Again, we have a quadratic of some variety. So let's see what we end up with. X squared plus 10x plus 21 equals 0. Okay, now this particular problem does indeed factor. What two numbers multiply to 21 and add up to 10? So let's factor this here. What two numbers multiply to 21 and add up to 10? 3 and 7, that is correct. So we're going to have x plus 3, x plus 7. Again, if you didn't know what that was, you can go ahead and use the quadratic formula, and you can find it that way if you like. Okay. So we're going to get two values here for x. We're going to get x is equal to minus 3, and x is equal to minus 7. All right. Okay, now I do have a very important note here. Okay, so this part here is going to confuse a few people, but it is important nonetheless. Now, we indeed did find minus 3 and minus 7. That part is definitely true. However, one of these answers is no bueno. Okay, it's no good. And the answer we're going to strike out is going to be minus 7. So we're going to take away, oh, I mean do that. Let's do this. We're going to take away the minus 7. Now, minus 7 has a very unique designation to it. Indeed, as you saw through the process, we were able to find minus 7 as an answer here after doing all the work. Okay, that part is definitely true. However, the one thing about minus 7 that the problem is that if I plug in minus 7 into here, I'm going to get, say, log of minus 1. The problem is that you cannot take the log of a negative number, no matter what base it is. Okay, so we can't take logs of negative numbers. So we have a unique name for solutions that we find that don't work in the original problem. So minus 7 is what we call an extraneous solution. So what is an extraneous solution? So an extraneous solution is a solution which you find does not work in the original problem. So some questions there will have some questions on the homework may have, well, what's an extraneous solution? Okay, well now you can say that minus 7 would be your extraneous solution. The real actual answer that does work, of course, is minus 3. That part is okay. That part you won't run into trouble. But with minus 7, you're going to run into a lot of trouble very, very quickly. So if the questions on ALEKS or the homework, they ask, hey, are you, is this what's an extraneous solution? Now you understand what they're actually asking for here in that particular problem. Okay. Okay, are there any questions about that so far? Nope. I'm going to do one more example from this section, and then we'll move on. Okay, let's go ahead and do one more example from this section, because it does have some importance. All right, bam. Okay. Now, the last question I want to do here is a specific question. So All right. So let's take a look at this question here. Log of 2x minus 1 equals log of x plus 3 plus log of 3. All right. So really quick here, just as a friendly reminder to everybody, if I just write log here, just like it says here, what base of log is that, by the way? What base log is regular log? That's correct. It is indeed log base 10. All right, so log base 10 is certainly the way to be. Oh man. Okay, so actually, have you guys noticed that there have been no skips today? I think this is working out. I made a big, like, background switch, and I think this is working really, really well. So there have been no skips today whatsoever. That makes me very happy. All right. So that's log base 10. Okay, so just as a reminder here, if you want to write log base 10, I know, I'm super pumped about it actually. Been working at this for a while. I jinxed it, right? Of course I did. That you jinx, I jinxed it for you. You can always refresh. I didn't jinx it for me because I watch my stream at the same time you guys do. So that way I can see if it freezes or not on your end. So I try and make sure that you guys are taken care of as best as possible. So that's how I know when it freezes for you, it freezes for me at the same time. But it didn't freeze, so yeah, that's good. Okay, let's talk about what we're going to be doing here first. Okay, so in this particular case here, we're going to go ahead and multiply here using our product rule. So we're going to have log of 3 times x plus 3. We'll have log of 2x minus 1, just like so. Okay, so we go ahead and put this together here. All right, so this is equal to log of 3x plus 9. And that's once again log of 2x minus 1. Now, this is one of the things we talked about yesterday, but it does help answer the next question over. I already answered this question technically, but it does, just kind of going back here for just a second. Let's go here. The one-to-one properties for logarithms. Okay, we did talk about that before in the last class. I just didn't really state it as that's the answer to the question. So if you're just kind of like filling in the blanks here, then let's go ahead and at least talk about that here real quick. I'll use this. So again, if we have log base b of x equals log base b of y, then x equals y. Okay, so again, this is our nice little one-to-one property here for logs. Okay. All right, so that's pretty much how that goes. All right. Not too bad. Okay. So basically what we're doing here is we're going to be pretty much doing the same thing here. We're going to be doing 2x minus 1 equals 3x plus 9. In effect, again, the logs just effectively cancel each other out. So using that one-to-one property there. So this log can cancel out with this log. Basically is what you're doing. And we could go ahead and solve just using regular algebra. So here we get x is equal to minus 10. Okay, now is minus 10 here? Let's answer the question. This is what you have to ask for every log question here. Is minus 10 a viable solution or is it an extraneous solution? So is it a real solution or an extraneous solution? Okay, I understand that. That's fair. Okay, so minus 10 is an extraneous solution. How do we know that? Well, we know that because if we plug in minus 10 into the original problem, we're going to get, say, log of minus 22. And so we cannot take the log of a negative number. That's not possible. So due to the fact that the domain of a log function is all positive numbers, minus 10 is definitely not going to work if we plug it into the original problem. So what that means is that minus 10 is not a real solution, although we did find it to be an extraneous solution. So your answer here is if they ask you, hey, what are the real solutions for this problem here? What we can put is no solution because minus 10 is extraneous. Or you may see this on the homework as well. You may see the big circle with a slash through it. So like that. So that is going to be, again, another way to represent no solution, just like so. Okay. Okay, any questions about that? Okay. So far, so bueno. Okay. All right, let's go to the next part now. So that's pretty much the end of section 4.4. So let's move on here to section 4.5, which is the last section of chapter 4. So let's look at question number 3 here. Question 3 says, what is the formula for exponential growth and decay? So we're going to be looking at applications of using exponential modeling of some variety, and this is the first said thing. So exponential growth and decay can be basically boiled down into one formula. So we're going to look at that formula right now. So that's going to be A equals A 0 e to the kt power. So this is our formula here. A is equal to A0 e to the kt power. Actually, hey, you know what? That's fine. That's fine, I guess. All right. Not a huge fan, but okay. It is what it is. All right. Let's define each letter here, okay? So defining each letter here, let's go ahead and take a look at what each letter represents because they have meanings. First is the letter A. just the plain letter A is going to be representative of the future amount. Okay, so the future amount here, after everything is said and done, that's the future amount at the end. A0, so A0 here is what we call the initial amount. So the initial amount here is going to be A0. T here is equal to time. And again, time is different for every problem. So it could be in minutes, it could be in hours, it could be in years, whatever the case may be. It just depends on the problem. Okay, so time can be whatever you want it to be. And then finally, there's K. All right, so K is a different representation here. K represents the rate of growth or decay. Now, how do you know it grows or how do you know it decays? Well, it's actually rather simple here with K. If K is bigger than 0, so let's say K is positive, okay? So again, by the way, just to let you know, K here is a constant, so. All right, if K is a positive number here, then that represents growth. If you just go the opposite way, K is less than 0, then that equals decay. Okay, simple enough. All right, K is positive, growing, K is negative, decaying. Okay. Okay, so, yeah. Okay, cool. There. Hang on a second, everybody. Trying to find the thing here. Okay, there we go. That's the one I wanted. Sorry, looking for the right example here, because for us to do this here. Okay, so we're going to go ahead and do an example here, and let's go ahead and see how that works out. Is that the one I want to do, or is there the other one? Okay. All right, that's fine. Okay. So the next example I'm going to do here talks about a very important topic here, a topic that all of you have probably heard about maybe at least once, maybe. So what's the practical application behind doing exponential growth or decay? Well, this has more to do with half-life problems. So that's what we're going to be doing here, half-life problems. So the next couple of examples here will reflect half-life problems. And no, I'm not promising Half-Life 3. Okay, that isn't happening. No. Okay. Anyway. Let's look at some half-life problems here. So I'm just going to type this out here. So let's say the half-life of a, let's going to do this here. The half-life of a radioactive element is 10 seconds. Okay. If 16 grams of the element was initially present. How many grams are present after 10 seconds, 15 seconds? Okay. All right. So we're going to ask two questions here. The half-life of a radioactive element is 10 seconds. If 16 grams of the element was initially present, how many grams are present after 10 seconds and after 15 seconds? Okay. So how exactly does this work? Well, let's set up the problem here in the way that we are given this information. First and foremost here, we have to talk about the initial amount. Okay, so let's go back here. Again, we're going to use our formula that we have here. All right. And again, our goal here is to go ahead and find that rate of decay. So, oops, I already did that. Okay. So the initial amount here. So let's take stock in what that is. What is the initial amount in this problem? How much of this element did we start off with? 16, that's right. Okay. We started off with 16. Now, let's talk about, we have an initial amount of 16. Now, for us to understand what's going to happen next, there is something that we need to do. Let's talk about one of the keys here into doing these half-life type of problems. All right, so one of the things that needs to be understood is that, let me think here. Hang on. Yeah, right. Okay, I know that. All right. So one of the things that needs to be understood is how much we're going to have left. And that's actually understanding the concept of what half-life actually means. Half-life, in actual definition terms, half-life is the amount of time it takes for something to get to half of its original mass. Okay, so the amount of time it takes for something to get to half of its original mass. So if that's the definition of half-life, okay, how about our ending amount here? Okay, what's our ending amount here in this case? How much is our ending amount here? That's right. So after 10 seconds, it reduces from 16 grams to 8 grams. Okay, this is after 10 seconds. So we actually answered the first half of the problem here. How many grams are present after 10 seconds? Well, we know for a fact that there should be 8 grams left after 10 seconds because that's the definition of what half-life means. All right. Well, now that we have that, what about 15 seconds? How do we find out how much of this particular element is left after 15 seconds? Well, that's a little bit of a tougher task. But we are going to use the fact that we know what the half-life is going to be here, since we know that it's going to be 10 seconds for every iteration. Okay. So how do we exactly do that? Well, let's set up our equation like we have up here. A equals A0 e to the kt power. What we want to do here is, what's the key? The key is to solve for k first, and then plug in the value for t that you are given. Okay. So solve for k first, and then plug in the value for t that you were given. So let's take a look at what that means. So what this means is that we're going to have a, which is 8, equals, actually, let's put it on the Let's put it on the big thing here. Boop. So we have 8 here is equal to 16. Okay, e to the k. Now I don't know what k is just yet, but I do know how much time it's going to take. It'll take 10 seconds, according to the problem, to go from 16 grams to 8 grams. Okay, so this is how we're setting up our problem here. All right. Now, what do you guys think? What should I do first? How am I going to solve for k here? How do we solve for k first? What should we do? That's correct, JTS. That's right. Let's divide by 16. So we got 8 over 16 here. So that's going to be 1/2 e to the 10k. Let's just rewrite that nicely. All right. So far so good. What should we do next? We're trying to solve for k. What comes next? That's right. That's absolutely right, JTS. That's right. We're going to take the natural log of both sides, just like we did in the last section. So here we're given natural log of 1/2. However, on the right-hand side, the natural log and the e will cancel out. That leaves us with just 10k. Now we can go ahead and divide by 10. Okay. Now let's go ahead and take a look at this particular problem here. All right. So we have natural log of 1/2. Okay. Divided by 10. Now you will get a negative number here because it is decaying. Okay, so let's write out what I have for k here. So that'll be negative 0.0693 147 181. All right, so negative 0.0693 147 181. Now, I do want to point out one very important thing in this process. Notice that for k, I did not round for k. Okay, so one thing for k here, unless it asks you in the problem on the homework to round, do not round for k. So I will put that as a very important note here in this case. Okay. Do not round for k. Very, very important. Actually, I should take that back again. Let's try this. All right, that's better. Okay. All right. So the reason why I don't want to round for k is because if you round for k with you know, like let's say you round it to negative 0.07, yeah, your answer is going to be off and then you'll be marked off wrong. So you don't want to be marked off wrong on the problem, so you don't round k. You can round at the end of the problem, but technically k is still in the middle of the problem before we actually find out how much is left after 15 seconds, okay? So that's actually rather important there. Okay, well now we can get to the end of the problem, because now we can set this up. we're trying to find out how much is left after 15 seconds. So we have 16, all right, e to the k. Now that we have this whole k here, that's going to be negative 0.0693147,181. And now we have our time t here given to us in seconds. That is 15 seconds. So we're going to put that in its own little set of brackets or parentheses there. And then we're going to get our answer. How much is left after 15 seconds? Okay. And so here we get 5.6569. Okay. So 5.6569 grams is what we get here for this problem. Any questions about that? Okay, good. All right. Okay, let's go ahead and do another problem here, okay, with exponential decay. We'll do one with exponential growth as well. So, all right. Okay. So, the next kind of problem here is very, very useful. If you ever wondered how people could actually track down an age of a rock or an age of a skeleton, well, you actually use exponential growth and decay to actually figure it out. So you can actually, again, you can figure out how old something is based on, say, certain elements that are contained within, say, skeletons or rocks and their rate of decay. So in this particular case, let's go ahead and work with carbon-14. Carbon-14 is a common element found in all skeleton bones. Okay, and so if you can check the rate of decay of the carbon-14 in a skeleton, you can actually determine how old it is. So in this case here, they give us already the decay model here for carbon-14, and this is the decay model they give us here. So it's A0 e to the, and I'm going to write this down here carefully. Okay. 0.000121 times t, where t is going to be time in years. Okay. So as you know, bones do not necessarily uh, are bones don't necessarily decay very quickly. So again, it's a slow decay there. Hence why you have the French catacombs still have a, still today. In any case, the important part here is, let's say we found out that let's say we found a skeleton here that contained 15% of its original carbon-14. So let's say we have a skeleton. We're doing an archaeological dig. The skeleton has 15% of its original carbon-14. Okay, so it has 15% of its original mass. All right, that's as much as we know. We're trying to find out how old the skeleton is. Okay, so if we're trying to figure out how old the skeleton is here, let's talk about what we have. Now here's the most important part, is right here at the beginning of the problem. Let's make an assumption here, okay? And let's say that the skeleton, so what's the key here? The key here is to assume we're going to assume that the initial amount here is equal to 100. So let's assume that the initial amount here is 100. So 100 for 100%. Simple enough. So if we assume that that's going to be 100 to start with, okay. Hey, Toast, how are you, my dude? If we assume that to be 100, what should that equal at the end of the day? What should that equal? This is as good as it's going to get, Toast. So 15% of its original carbon-14 is left. So how much should be left over after all that time has passed? What's 15% of 5 of 100? Ooh. Boy, 15% of 100? It's tough, man. Okay, that's correct. Okay, 15. That's right. Now, technically, you could put 1, and then you could have 0.15 planets, so that would be fine. So if you put A0 as 1, and then the answer would be 0.15, that's fine. I'm just trying to show an easy way to just kind of see the numbers here really quick. Either way is fine, though. No problem. So we're going to go ahead and divide by 100 here. So we're going to have 0.15 here is equal to e to the minus 0.000121 times t. Then we'll just repeat the process like we did in the last problem. Take that natural log of both sides. That cancels out. And now we're going to have, again, natural log of 0.15 equals negative 0.000121 times t. And then we'll just divide here. So pretty much after this, it's calculator time. Okay, so let's get a time t here. So we got natural log, divided by negative 0.000121. Okay. And so here we get a time t here of 15,678.68 years. So a little over 15,500 years old is how old this skeleton is. All right. All right, good. Are there any questions about that? Nope. Okie dokies. Let's do the, let's go ahead and do the next one here. All right. So that's the answer for number 3 there. Let's look at number 4. Number 4, what is the logistic growth model? So the logistic growth model talks about, say, population growth. All right. If we talk about, you know, gosh, I should read this book here. Hang on. Let me read this first line of this book here. Logistic growth models. All right. From population growth, which is true, to the spread of an epidemic. Nothing on Earth can grow exponentially indefinitely. Growth is always limited. Man, this book here got it right. The irony is so true. It's like you have a finite space on planet Earth, so yeah, you can have a limited population. That part's true. And then it's like, oh yeah, the spread of an epidemic. Yeah, that didn't age too well. Yeah, that kind of sucks. That's pretty bad. I'm crossing my fingers. I'm crossing my fingers. Okay, that this goes away. However, I mean, I did watch AEW Dynamite last night, and that was fantastic. That has been the thing that's been keeping me afloat for this whole pandemic, is watching AEW Dynamite and wrestling. I can't go wrong. Can't go wrong with watching wrestling. So, especially after yesterday's episode, man, that was great. All right. Okay. What is the logistic growth model, though? Let's talk about that. Okay, so the logistic growth model can be modeled like this. Again, it's like AE0 e to the KT, only it's written like this. So excuse me, A is written like this. A is equal to C over 1 plus A to the minus BT power. Okay. And I'll throw in a couple of other things here, obviously, because I'm just throwing in letters at this point. Okay, so a couple things about this formula here is that A, B, and C are just constant numbers. So A, B, and C are constant numbers. So they're just kind of random constant numbers. Okay, that's fair. What's your favorite series so far, Planet? I have to ask. Okay. All right. So there's two other conditions here. A, B, and C are constant numbers. B is always bigger than 0, and C is always bigger than 0. So A, B, and C are nice positive numbers there at the end of the day. Okay. Holy irony, Batman. All right. Let's take a look at a problem here. Yeah. I'm going to try and do a problem that... yeah. All right. Okay, so we have a logistic problem here. Let's do an example. Okay. So we're given a logistics growth function here. And let's write out that logistics growth function, which is going to be f of t. F of t, by the way, is the same thing as a. So, where is it here? No, wait. I just saw that. Oh, okay. That's fine. All right, so that's going to be, actually, let's go with, change my mind here. Let's go with x for that. For important reasons, I'll say. Okay, so let's say this is our logistics growth function here. 90 divided by 1 plus 271 e to the minus 0.122x. I'll go ahead and read off this problem here because it is a word problem. So this is a logistic growth function here, which models the percentage of Americans who are X years old with some coronary heart disease. So the important part here is that X here is the is years old. Okay, where they have again, this represents a percentage of people who have coronary heart disease. Okay, so let's look at several questions here. The first question here is that what percentage of 20-year-olds have some coronary heart disease? So 20 years old. So how about, again, in this case here, x is equal to 20. All right, let's round to a tenth. All right, so round to a tenth here. Can anybody tell me, put this on your calculator here, again, replace x with 20. Can anybody tell me here what our answer should be if we plug in 20 into this problem? Basically, this is like a check to be sure that you plug this in right in the calculator. It's not hard, it's just, again, getting that correct number. So okay, that's correct. 3.66, or again, 3.7%. Good. That is absolutely correct. Very nice, JTS. All right, let's do one more here. Well, that one is just requires more work. Okay, so how about x is equal to 80? How about 80 years old? How about 80? What do we get there? If you're 80 years old, what's the percentage in this case about this type of model? 88.6, that's correct. Good. Nice job, my dude. 88.6%. Okay, excellent. All right, good. So that's how we deal with the logistical growth model. Again, if it tasks you for what age, you're going to go, of course, take the natural log of both sides, do the things and whatnot. But yeah, that's for that problem there. Okay, there is one more part here, but I'm not going to have time to do that because that requires a lot more time to do. All right, now the next part here that I have to talk about, because I do have a very important thing we need to discuss. So what the heck is this? No, come back. All right. All right, so that's gonna be what? That? Okay. All right, so we have this first there. So I just gotta check something here really quick for you guys, and then I have to make an announcement about that. Okay. Let me make sure about that. That's correct. Okay. So we got this and got that. Okay. Okay, so this is basically going to be like Unit 4. Now it's kind of weird because Unit 4 is kind of split up into like a couple of parts there. So, okay. I have to make sure I get this all down properly, proper like. Okay. So I'm bring this over once again. Okay. So let's go ahead and I need to set a new due date here for the test here. So what I'd like you to do is do the fourth test, okay, the Unit 4 test, which is the third test that you see here. Okay, so we're going to quick edit this. All right, so I'm going to make this test due, why is the start date today? That's terrible. Let's make that today. Let's have this test be due on the 1st. Okay, so on the 1st of November, test number 3 will be due. Okay, um, and then what we'll also have here is we're also going to have, of course, I'm going to put up the practice test here. So let's do that. Where is it here? Here we go. Practice test. Okay, so obviously you can start on that today. And of course, we'll be due the 1st. Okay. Wait, no. That was, I wanted it to be the 1st. Yeah, that 1st. Okay. Like to enable that. So I'm just checking to see if this is okay. Yeah, that's open. Okay. Okay, now let's go ahead and wait, why is this give me a second, guys. Like, I want you to see this because it's kind of like an important thing for you guys. So it's like really complex to do. Wait, what? No, test 2 was for what did I do? Hang on a second. Test 3 is Unit 4. That's fine. Practice test 3 should be... Oh, okay, okay. Thanks, Gerda. Yeah, you're right about that. That's why I do this in front of you guys, because then it doesn't look like I'm a derp. It's a lot... You're like, it's a lot easier if I just don't look like I'm dumb. Much, much easier. Okay, let's enable that. And then I gotta disable the practice test 4 there. So let's do that. Okay, and then for these homework things, okay, I'm going to effectively change this here for number 4. So unit 4 is kind of in like a couple of parts, which is a little weird. So I'm going to kind of change those dates there. See if this works. Blah, 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 blah. Things. All right. So unit 4, part 1, part 2, part 3, that'll be due on the 1st. So homework is for points. Don't forget about that. I do look at the homework score. Homework is definitely for points. So don't forget about that part there. Yeah, Unit 5 in this last part for Unit 4. I'm going to open this up, obviously. But yeah, I'm just going to be like, okay. You'll have a chance to work on that as you please. Oh, really? That's kind of dumb. All right, fine. Let me do dumb things because the system is dumb. All right. That should be fine. Let me check that really fast. Yeah, that's fine. Okay. Oops. Oops, what? What did I do something wrong? No? Okay. Sorry. If I did something wrong, just let me know, cuz that's why I show this in front of you, because I want to be like, hey, I want to be super transparent that it's open and stuff. So, I want to be like, "Oh, okay. What'd you do, you stupid moron?" And then I'd be like, "No, I swear, I'm not stupid moron." And they'd be like, "Yes, you stupid moron." And then I'd be like, "No, not stupid moron." So, let me change this though. Blah, blah, blah. Reasons. Um, yeah, that's cool. Okay, good question, Planet. So I don't grade the homework. I grade the homework based on the percentage that you complete correctly. So it's not all or nothing. I look at the percentage that you completed correctly, and then that is the score that I give you for that unit. To be as transparent as I can be. So okay, that part's fine. This is okay. Okay, so that's okay. Practice test 3. Okay, we're good. Practice test this. That's fine. Okay, that's fine too. Okay, fine. We're good. Solid like a rock. All right. I approve. All right. That works. Okay. That should take care of everything there. Now that I got that all set up and ready to go. Yeah. Go team me. Can you ask which percentage goes for 4, 3, 2, and 1? If you're talking about like the parts there, I look at your overall part, not part, but I look at the grade book and I see what your overall percentages for the for each unit, and then I basically spread out those points between all the sections in that unit that you see on D2L. So that's how I give you a fair amount of points there. Does that make sense? So I don't want to show off the grade book here because you know, that has personal information on it. But what I can tell you is that yeah, I just look at your overall percentage and then start recording scores after that for each unit. Any other questions before I head off here? I mean, is which percentage range is for each grade? I'm a little confused, Planet. Sorry, I'm a percentage range. Are you talking for like A, B, C, D, or I mean that? Like, let me actually look at that here really quick. Let me take a look. Oh, okay, I see what you're saying. All right, I get it. 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 So like, okay, make sure about that. Okay, so what it will do is, and to answer your question a little bit more fully, yeah, yeah. So let me at least describe what it does here. The percentage that it gives me here, okay, on my grade book, okay, is going to be the percentage that you completed, okay, and that is for the all the parts put together, okay. So um, so when I look at the grade book here for for this, then I take a look at the gradebook. I say, okay, this is the percentage that you got completed for the homework for all the parts put together. And then I take those sections, I see how many sections that there were in that particular unit, and then basically I divide that up by 5. I did, you know, and then I put out the same amount of points for each section here. That's how I essentially do that. So if I gave you, say, 5 points for each section, for example, if I gave you 5 points for each section, that means you got 100%, right? If you got 90%, you take 5 points, take 90% of 5 points, and you get 4.5 points for each one. Okay, okay. Then I will take a look at that, and I will see. I'll see if it did it. What did it change to? If actually, no, hang on a second. whisper me about what that changed to, so I can take a look at that. Okay. Don't tell me over chat, but just whisper that to me. Um, and then I can tell you. I can see what I'm looking at here when I start recording scores and stuff. Yeah, I prefer everybody's information kept private. So, all right. Any more questions? But because if that's it, that's where we're going to take care of it for today. Everybody, I want to thank you all again for coming out to the stream. All right. Um, Planet, you can stick around. That's fine. All right. Thank you again very much, everybody. Everybody, have a wonderful weekend. I hope you really enjoy yourself. Okay. Please take care. All right. Have yourself a great one. All right. And relax. Okay. Take your time. Next time, guys, we're going to go over a review for this test and one more thing that I need to talk about. So that'll be on the agenda here for next Tuesday. All right. So doing a little bit more review here will be all good. Planet, wait, don't go. Buddy, you're supposed to whisper me. Whisper. Yes. Planet, you stay. All right. Everybody else, have a great weekend. Take care of yourselves. All right. We'll see you later. Okay, bye. Planet, my dude, you gotta whisper me. Hit the little whisper icon. It's like that little message box at the top of your screen there. I sent you a little whisper. It should have an icon with a 1 next to it. Did you get the whisper, Planet? Okay. Can you send me back what I asked for through the whisper? Okay. Thanks, Ben. Okay. All right. All right. Let me check that for you, Planet. Okay, because I got it right here. Okay. Uh. Yeah. Okay. No problem. I just wanted to be sure that that was taken care of. Okay. No, nothing. No, look, don't bother. It's not you bothering me. It's you actually, that's a legitimate question because of, the weird funkiness that is Alex. So it's not your fault. That's just how the system is. But yeah, no worries. You're just fine. Okay. I hope. Wait, why? Why? Oh. You're cool. You're cool. All right. No worries. No worries. You're cool. You're cool. All right. It's all good. Let's put those fears to rest and focus on that test. Hey, that rhymes a little bit. Um, you see, like, hmm, hmm. No, it's just look, you gotta you gotta give it up to reason. That's all. That's how it is with computer systems. Sometimes it's really funky how they grade. My math lab does the same thing sometimes. So I could totally understand how you feel. It's like you get a little panicky or nervous because it's like, oh, that work suddenly goes away because of something I can't control. Totally get it. But I'm here to put those fears to rest and make sure you have a nice peace of mind at the end of the day. That's all that matters. Hey, no problem. I'm here to help, okay? I hope you have a wonderful weekend, though. It's okay. Me too, sometimes. Me too. I think everybody can say they've been guilty of that. But that's why you asked, just to give peace of mind. So, what I would like you to do now is to not overthink this weekend and just have a nice weekend. Just enjoy yourself, okay? All right. All right. Thank you so much. All right. You take care, and I will see everybody later. Okay. Have a wonderful day. All right. Bye. Take care. We'll see you next week, okay? Bye.